tell you about some work I did at my home university, the University of Toronto, in the chemistry department. So we're trying to resolve this mystery, which is why, if you measure the conductance of a molecule one way, you get a certain answer, and if you measure it a different way, you get a completely divergent answer. And in particular, not just the answers are different, but they have different dependence on the number of atoms, which is really mysterious. So the traditional old-fashioned experiment for measuring the conductance of a molecule or anything really is you just put it between two metals and just run a current through it and then measure the conductance, like with a resistor or however you do it conventionally. And if you do this, you find that the conductance falls with 1 over n, like with 1 over the number of atoms. So that means the electrons are spending, the lifetime of the electron on the molecule is increasing with n. And the fancy new experiment you can do, which needs expensive laser technology, so it's only recently that they've been able to do this, is that they can manage to inject a single electron and watch its dynamics with spectroscopy. So if you do this and then if you watch the lifetime of a single electron on this molecule, you find that the lifetime increases with the square of the number of atoms. So sure, these are the exact same experimental conditions. So you shouldn't expect the same exact number, but it's really strange that the dependence on the number of atoms isn't the same. So that's the mystery we're trying to resolve with and we're going to do a theoretical study, model the system and see if we can recreate this behavior. So the first thing we're going to do with our model is ignore most of electron dynamics because it's too hard. In electron dynamics, you have all this stuff with orbitals and wave mechanics and all this stuff, and we don't care. We're going to say if a molecule has n atoms, it has n states, where each state means you're near this atom. You're near atom 1, you're near atom 2, you're near atom 3. And it doesn't really matter where you are. If you're near atom 3, we don't care what orbital you're in. We don't care how long you've been there. In fact, we're just going to say if you're near atom 2, you have some probability to jump to being near atom 3, or some probability to jump to being near atom 1. This is our model. So we went from that picture of a molecule and orbitals and all these things to this picture, which doesn't look very much like a molecule. But if we work it out, we'll see that somehow this manages to recreate the dynamics. And in fact, it manages to resolve this mystery happening in dependence on the number of atoms. Okay, so we can write it down. Now that we have a nice model, we can write it down. We have some rates. We're going to write down these rates, these k's are the rates or the probabilities. So if you're on state 2, if you're thinking about, okay, how is my system changing? What's the rate of change at state 2? Well, it's the contribution going in, so population here times that rate, plus population here times that rate, minus the contribution going out, which is similar. And we can write a very nice, an incredibly nice equation for each state. So the rate of change, it's what I said before, the rate of change at a certain site is the rates in minus the rates out. And if you've taken matrix algebra or linear algebra, you will like this very much because this equation is linear in T. In T, the population at a certain time. So we write this very nice equation where this is a matrix of rates, this is a vector of the change in the population at a certain time, and this is a vector of population at a certain time on each site. So this is very nice because now we can actually solve it instead of staring at wave mechanics equations. So then now all we have to do is think about how we can apply our model to those two different situations and see if we can resolve this mystery. So in the first experiment, we're putting a voltage across. We're going to put a voltage across and let the system come to a steady state. So that means that at each site, the change in the population is 0. There's no change. Okay? But of course, we're kind of artificially putting in electrons. The effect of our current or our voltage across this molecule is to artificially put new electrons into the system. So the change at site 1 is not 0. It's equal to the flow in, which of course is the inverse of the time it spends. on the molecule. So again, just in matrix language, the change is that vector over here, which is 0 in every state except the first one. Okay, and we can also look at the other experiment, in which we're putting a single electron and then we're waiting for the average time for it to leave, for it to go out. And you can just write the integral for how long. Okay, so well, the amount of time it spends in the whole molecule is the sum of the amount of time it spends on each state. And you can write that as an integral here, and you should believe me when I say that that's the solution. You just have to. I can prove it if you ask, but I don't want to. And, well, what's this initial state vector? Initially, we have a population. The particle is certain to be on the first state and is not on any of the states. So it's on the first state with probability 1, and in the other states with probability 0. So this P initial here is this vector, which means if we take this vector of residence times, of average residence times, and apply the matrix of rates M to it, we get this vector. Okay, this doesn't have like a physical meaning anymore, because it's not like a rate of change anymore, but it's very suggestive because it looks almost like our other vector from the first experiment, which is nice because it tells us how they're related. So it turns out, in fact, that the vector average times you spend on each site is a rescaled vector of the steady state population of the molecule, which doesn't really have a physical interpretation because the steady state vector, they don't even have the same units, right? Like, you know, the first vector up there is like the integral of the population over time, and the second one is just the population at a certain time. But, I mean, we're already kind of interchangeably using like populations and probabilities and rates and probabilities, so it has a nice intuitive answer, not like a really physical one. But anyway, there are these two different times, the single electron average lifetime and the steady state lifetime are related. And they're related by the sum of all the sites, the sum of the populations in the steady state vector. Which is nice because it resolves our mystery, because if you increase the number of sites in your atom, well, each atom holds about the same population. So the steady state, the total population of the steady state increases with n. So the steady state, the single electron lifetime will increase n times faster than the other lifetime. So that explains our mystery. One of them was increasing with n, the other one was increasing with n squared. Well, where's this extra factor of n coming in? It's coming in from this steady state population, which is increasing with n. Somehow this model, which doesn't look at all like a molecule, is recreating like qualitatively at least, the dynamics of our real system. And if you do more work and like think about whether or not the rates we're getting are physical compared to an experiment, you find that they do. So you find that, yeah, this is the reason. Like this is a reasonable model for that. And up there is it's just a graph. Well, maybe it's not so clear. Everything is log scale, so the numbers are the slopes, are the exponents. So in the steady state one, always increases with n to the first power, and in the other one, it depends. The dependence on n, well, it depends on, you know, how populated the steady state is. So when they're all equally populated, it increases with n squared, which is at least that. That was shorter than I expected, but that's fine. That's us. And that's me. And if you want to read more, you can.